help?
One thing that I saw just looking at the elastic strain energy in equations 1 and 2 right there is that in class last time we were saying that it was lambda at 0, but then I was looking at those today and they just say lambda. And so I was wondering if we could maybe make, I don't know,
Make a
make them the
decision?
same across it all.
It'd be good to make a decision.
Yeah,
Yeah, this should be lambda at 0.
okay, perfect.
Do I think all the do you, Caleb and Kyle, you guys have edit privileges, right?
Correct.
Yep.
Okay, can you guys go in and here's the first one, is that it should be lambda at 0.
Sure, I'll grab that.
Just make those.
Thanks, Caleb.
We've got lambda.
Dr. Scott, could I ask you to clarify the significance of lambda at 0, please?
Yeah. Okay, so this first equation, the reason I write it in this more general form here with the actual integrals is just to help orient you to the notation. Because in general, this won't be a one-dimensional problem. It'll be a multi-dimensional problem where these boundary integrals will have more significance. So the first line is really an introduction to the notation. On the second line, I actually write down what this integral means in 1D. In 1D, it's just it's either endpoint, so it's just a point. There is no integral. So you take the integrand and you evaluate it at the endpoint. That's what, so I've taken this integral here and converted it into what it would look like if the integral was just a single point. Same thing over here. This is at x equal to L. It's just a single point. So you just evaluate your displacement at L multiplied by this constant value h sub L. So that's what's going on there. Was there any more to your question there that I missed?
No, I just had missed that we were applying it on the x equals 0 end, and that's where the at 0 came from. I thought maybe it was a scalar or something like that. Yeah, so thank you for the clarification.
Yeah, just evaluate it at the endpoints. Okay.
What is the difference between u at 0 and u not? Is it a time difference?
So what's going on here is, like, if this, let's say that this actually, the actual model was a bar like this. Whoops, that's kind of wonky, but let's just say for kicks that it looked like that. Then u naught in this case would be equal to 0, which means that this is an initial displacement in the x direction. And so if the initial displacement was 0, like it was fixed on the left end, then u naught would be equal to 0. So this just means that there's some prescribed displacement that at point 0, and I'm just calling that constant value u naught. It's not, this is just a number, it's not a function of x. What I'm saying is that the displacement, which is a function of x, at x equal to 0, should be equal to this given value, u naught.
Is u naught referring to the location or to the initial?
It's the displacement at x equal to, it's a prescribed, what u naught is it's saying that the displacement, I'm trying to set the displacement at x equal to 0 equal to u naught. That's what that notation is.
Okay.
It's just a number. It's a prescribed displacement. I mean, this could be, if this was like, if U naught was, let's say it was equal to like 2, what that would mean is I take the whole bar, displace it to the right 2 units, and then solve the problem.
Yeah.
So it's just a number, a value. Okay, other questions, not necessarily even on this section.
I have a question.
Okay.
What is capital pi? Right, the first part of the equation. What does, yeah.
So this symbol is often the symbol used for potential energy.
Oh, okay.
So it's just a symbol saying pi is a function of u and lambda, and it's we're setting it equal to this expression here.
Okay.
Yeah.
That makes sense.
This is great questions, guy. I know notation is hard. Like this, there's a lot of notation. A lot of you have never really had a lot of exposure to mathematical notation. So I know there's questions here. These are not like trivial questions. These are important. Otherwise you can't like communicate or read the document, let alone understand it.
Yeah, along that term, so up on that first generalized form, you have the very first integrands over omega, and then it's d omega. You also have derivatives of u with respect to x. Is that, when you're writing that notation like that, like if this bar was not, we're not simply solving in the one dimensional of x, would that still be u derivative with respect to x, or would it be more of a volumetric type integrand or
Yeah, it would
derivative?
actually be the gradient of u in general.
Okay.
If again, this is just to help. This is just a fixed notation, this more general form. It's still a one-dimensional problem. And so, but if I was actually doing three-dimensional strain energy density looks like 1/2 in the linear elastic setting, it is epsilon, where these are matrices. So this is a strain matrix, stress tensor, strain tensor. And so this is what strain energy density looks like in general. So epsilon is, in general, it's commonly a function of the gradient of strain. And this notation is a contraction. It's kind of like the generalization of the dot product to matrices. Again, this is just an aside, but just trying to answer your question the best I can here. And then stress is a function of strain. So anyway, that's what it would be like in multi-dimensions. And in just a little while, we're going, once I get done with a few more things in 1D, there's going to be a mathematical excuse me. There's going to be a mathematical preliminaries 2, where I'm going to introduce all of the tensor and vector algebra and calculus. So then we're ready to go into nonlinear continuum mechanics, so you'll know what all these symbols mean. You probably have seen them at some point in the distant past, like the gradient, and but we'll make it a lot more concrete for you, and it'll be a good review. So Eric, yeah, in general, in multi-D, you have things become gradients in that case.
Dr. Scott, I had a question in regards to, I guess, equation making. I've noticed that in a lot of my previous math courses that I've taken, typically they'll just give you an equation and they say, here you go. And you're like, great. And then they say, do stuff with it. And I'm kind of wondering if in this syllabus or if we'll get more intuition as far as how to connect writing an equation with what we're wanting to do in simulation. I feel like that is something I haven't really grasped.
So is your question like, where do the equations come from?
I'm kind of wondering if we'll develop an intuition or if in this class as to how to come up with the equations to accurately model our problems that we want to model. Or is that something that we just look in a theory manual in a certain simulation solver in order to actually see the equations written out?
No, no, of course not. That wouldn't be that. You know me better than that, Lindsay. That would not be very satisfying to me at all if that was the level of. Yeah. So these equations, they come from somewhere, and they come from the way that, at least in a continuum setting. So the first half of the course, I'm going to like say, okay, here's an energy, strain energy. You all kind of have some intuition about strain energy. And then we're going to do the numerics and talk about like the consequences. As soon as we're done with these few one-dimensional sections, then we're going to do, the way the course is going to work is we're going to have a math prelims 2, which is going to ground you in, like I say, vector and tensor algebra and calculus. And that will then prepare us to go into a subject called nonlinear continuum mechanics. Nonlinear continuum mechanics is the study of basically the motion, conservation of quantities in continuous media. And it's in not, whoops. The erase button is dangerous. So we have nonlinear continuum mechanics, math prelims 2. It's in here, Lindsay, that I'm going to show you where every equation you've ever seen comes from. So every equation that like you've ever done in engineering comes from these basic principles of nonlinear continuum mechanics and conservation laws. And this is actually like, we're going to get to this, but this strain energy is actually what it's saying in multi-dimensions is that the divergence of the stress is equal to F. This right here is conservation of linear momentum. So secretly, I'm already introducing you to conservation of linear momentum, even though you can't see it yet. This here, nonlinear continuum mechanics, I'll teach you enough to where you can see where all of these equations come from. And from these basic principles, we can do all the elasticity, we can do fluids, and I would put like acoustics maybe under fluids. We can do electromagnetics. We can do any of these applications all come from a common root. And so once you kind of gain a mastery of this subject, if you're a serious finite element person, you're an expert in nonlinear, you have an expertise in nonlinear continuum mechanics. Because if you have a new physical model, these are the principles we use to derive the governing equations. And so, so we're gonna do this and then this, and then after we do the nonlinear continuum mechanics, we will derive the theory of elasticity in its full generality. Well, we can go as far as you want. We can derive the full theory of elasticity. We can derive Navier-Stokes if you want. And then from there, we can derive finite element methods. So the answer to your question is, Lindsay, if you're serious about this, you should know where everything like comes from, you know.
Yeah, no, that's really helpful. I just wasn't sure if we were planning on talking about it in this class, and it's an intuition that I have still in need to develop. So it's exciting we're talking about it.
Yeah, and I'm gonna go, I mean, this may be, I'm just gonna keep going. I'll go this semester and then next semester, and then I'm gonna go into the summer. I'm just gonna like keep going until I get all this stuff down. So you guys are welcome to just keep coming until I'm done. So anyway, yeah, because this is really beautiful, right? I mean, once you get into the nonlinear continuum mechanics and general geometries, then all this stuff we're learning with splines really takes on a life of its own, you know, and how you approximate these theories. But all by itself, it's very satisfying to understand, like, okay, there's conservation laws, like conservation of angular linear momentum. There's these are the big ones that kind of govern mechanical problems, and there's other equilibrium statements that you make when you start involving temperature and anyway, but it all comes from a common root. This is called mathematical physics sometimes. So yeah, we're leading up to that. We got a couple more months of this 1D stuff before you're ready, and then we'll jump into the multi-D stuff. Okay. How else can we help? I was going to ask you, you may not quite be here yet, but anybody have any questions on these algorithms? Like, a big part of this class is like, I'm going to be telling you like, oh, here's all the equations, and then you're going to be turning those into algorithms. My experience over the years teaching students this material is that's also another big conceptual jump. Like, how do you, like, in your mind, how do you take an idea and turn it into an algorithm? Any questions on this algorithm? This is the last homework assignment in 3, is I have implement an algorithm to compute the best approximation for all these different bases and then plot different values. So I give you kind of this is kind of like a pseudocode framework. It's not every detail, but the fact that there's no questions indicates to me that you might not be here yet, because if you were, you'd have a lot of questions. Anybody here?
Yeah, I do have questions.
Okay, great.
So I get the parts of the compute quadrature, weights, and points, and I looked at the forum as well, and basically just kind of hard code those in.
Mm-hmm.
However, I don't know what to do to go about deriving the bases that I'm going to be using for these equations and
Yeah,
geometry.
So this guy right here.
Yeah, it is a pretty big jump looking at the pseudocode to try to then put it into what I'm using is MATLAB. So
yeah, so compute basis. Let's just talk about this. Let's say you were going to do let's just say for kicks, you were wanting to do the Bernstein basis. In this routine, right, it takes some location. Yeah, being able to do the actual algorithm development is a big part of this class too. This is important to me that you can get down to the practicalities here. So n is the degree, and then I'm passing in a value of xc. And so let's say you're doing the Bernstein basis. Then what you're going to do is, like, the easiest way would be to have like a switch statement in here. If n is equal to like 1, if it's degree 1, then you're going to create a little vector of base. So you'll have two basis functions, and you'll evaluate the first one at xc and the second one at xc, and stick them into some like array that you'll return. And then you'll say, like, else if p is equal to 2, then you'll have 3 of them, put them in the array, and then you'll return the array. So I don't know, depending on your language, maybe you'll return it, the signature of the function will look something like that. So that's like the simplest way, is you just have a huge switch statement on degree, and then in each degree you simply hard code, like, you know, like 1 minus xc. Anyway, you just literally hard code those equations, evaluate them at xc, and put them in array and return them. So that's the simplest way. There's actually like expressions for Bernstein bases in the notes for any degree. So you could write that down. That's a little more beautiful, a little more compact and concise. So that's another way to do it. And so you'll return an array, and that array will have basically basis function 1 evaluated at xc through basis function, like, maybe n, I guess there's n plus 1 of them. So this is just a vector, you know, an array vector, same thing. And then you'll return that array right here, and then you just index into that array as you go through your looping structure. Does that kind of answer your question, hopefully, a little bit?
Yeah, and so is this xc, is this our xci? So the
yeah,
the
and
quadrature
then
points.
yeah,
Okay.
so you have to decide your interval. Maybe you've standardized your code to where all of your xc's are going to be between -1 and 1. And then you'll have to make sure that you're evaluating your Bernsteins in that interval. And there's, in the notes, I show you how to, the Bernstein polynomials are normally written on the 0-1 interval. And in the notes, I give you the transformation to -1 to 1. It's just so that they need to be written in the interval, the same interval that you're taking your xc's from. Okay, so we would just use that transformation just as if we were doing some kind of change of variable to get into a -1 to 1. Okay. Yeah, and you need to go to look at for each polynomial basis, look at the canonical interval that it's defined under, and transform them to some standard interval that you want to use for your quadrature points. Usually it's -1 to 1. And that is nothing more than a change of variable. Okay, and then once you've got that, you can compute the geometry. And at this point, go ahead and compute it however you want, right? Like, because there's no derivative, well, there's this piece of derivative information. Your geometry can be, you can write it any way you want, right? Like, if your geometric interval, let's say, is a to b, That's what you've chosen for your geometry. And then, you know, you have -1 to 1 for your C coordinate. This is your X coordinate. And then there's some change of variable function right here. Then you can just write this down, right? This is just, maybe this is just some linear, it's just some A x C plus B. You solve for, or maybe I'll do it C1 plus C2. Solve for these coefficients C1 and C2 so that you get the mapping between -1 to 1 and A and B. And then you, for an XC value, you just evaluate this and that returns X. And then the dx dxc is going to simply be, in this case, it would just be C1. It's a constant C1. So just do a linear transformation for the geometry, right? The geometry is this function is really all that it is. It's the change of variables function from the C coordinate to the X coordinate. So again, you can just kind of hard code that in. Later on, we'll generalize this a little bit, but this is a good starting point.
Thank you.
And so for this simple approximation problem, that's about it. That's about the extent of the, there's just a quadrature routine, a basis function evaluation routine, and then like the change of variables or geometry mapping routine. And then it's literally just this piece of code that I've written here.
So Dr. Scott, just to clarify, that compute geom function is that change of variables and includes an array of the derivatives?
In this case, it's just going to be numbers because it's 1D. So you're saying, given a quadrature point XC, return the corresponding X. That's this guy. And then let's say C is right here. So maybe this is X, right? And then you also need the change of coordinate. You need the derivative because you're doing a change of a variable on the integral. And so you compute, you need dx dxc. But that's nothing more than taking the derivative of this linear polynomial.
Okay, that makes sense. Thanks.
Yeah, so it's kind of like, I like these little coding assignments because they kind of force you to, it makes you take the stuff you've learned, and it has to be pretty concrete in order to write down an algorithm because it's really precise. Okay, well, let's stop there. I appreciate the feedback on the course and your questions. Keep moving ahead. And on Monday, we'll keep driving our little finite element method, and I'll add some more homework problems too, if I can get to it this weekend. If not, it'll be early next week. Okay, thanks everybody. Appreciate it.
Thank you.
Thank you.
Thank you.
Thanks, Dr. Scott.